Next we have my good friend Michael Kluge. He's working at the Center for High Performance Computing at Technische Universität Dresden, with parallel file systems for more than 10 years now. Usually chasing topics like performance analysis and debugging, he currently focuses more on how to design storage systems in the future and on how to make the advantages of big data technologies available to HPC users. In addition, he currently manages the installation of TU Dresden's new HPC system. Ladies and gentlemen, Michael Kluge.
Rock on. Thank you for the introduction. Okay, I will at first talk a bit about ZIH, our computing center, what we're doing, and our new machine, and then a bit about the performance analysis tool that we're using in conjunction with Lustre. So we have actually to get funding for HPC machines in Germany, you have to have own research agenda, and we have two main topics. One is performance analysis, and the other performance analysis. Computer architecture is basically one of our main research areas, and the other one is energy efficiency. We also participate in a few standardization efforts, so we have members in OpenMP and OpenICC committees. And recently we were awarded one of the two big data competence centers in Germany. So there was a call, I think last year was it decided, and we're going to provide big data services for the scientific community in Germany, and we'll build up a service center that will provide that over the next years. So being a university in Germany, or being a university at all, we have a bit of a zoo of computing systems. We have currently 10 gigabit backbone, 100 gigabit backbone actually with the new data center. We have 250 gigabit uplinks to the world, and the build system which is currently installed is a bit smaller than what Hamburg actually has, and we have also a SGI NUMA system, and we have storage. HPC storage in our center is Lustre since 2006 or 7. We phased out the last SGI CXFS file system about a year ago, and even the SGI system. So we cross-mount all Lustre file systems on different machines. So we have SGI, Macware, IBM My Dataplex, and they're all running, or they're all having mounted different Lustre file systems. So the system that is currently installed, we also decided when we went out with a proposal to install different islands. So with the idea not to have full fat tree, but to have some island will always work, and you have a full fat tree within each island, and then a thinner connection to the other islands, and also to the storage. From the storage perspective, we will have an SSD in each node, and we have a global shared standard big scratch file system, and also a shared SSD file system, where Bill is currently fighting to get the 1 million IOPS. That's I think currently the biggest issue to get there, but they're on the way, and I think it will happen. So when we wrote a proposal for the DFG to get the funding, what we wanted to do is basically tailor file systems toward users. So that's similar to what Mark Stearman said yesterday. You want to have a bunch of servers, you want to have storage, kind of, maybe not really a virtualization layer, but you want to put stuff together in a way that the users don't interfere with each other too much. So we have, for example, that problem, we have a simulation guy that can fill up the file system in about a week. And whenever he runs, there's another guy that has laser pulse simulation. And he, at the end of his simulation, he writes 6 GB of data. And whenever the other guy is running, it takes hours to write the 6 GB of data. And when he's not running, it's like done in normal time. And I couldn't figure out what to do, but if we would assign them to different metadata servers, maybe in the first run to different OST pools, that would, certainly give the other guy way more predictable performance. And as we were doing performance analysis all the time, we want to collect all kind of access statistics from the system, analyze it, and then decide how to actually configure the system so that basically to minimize the global I/O time that all the users experience, so that they have more from the runtime. So of interest to us is basically the whole stack, starting from the application with all the application I/O requests, down to the storage RAID array with all the LANs in it, with the network interfaces, with the chips in the RAID arrays, usually with all the links in your InfiniBand network. And we want to record it very often, basically. So 5 to 10 second intervals was something we were thinking about, and we want to keep the data on that level for at least 1 or 2 years, and then analyze it and create metrics from that raw data and see what we can learn from it for designing the next storage system and how to divide the system between the users. So in your HPC file system, you have nodes, networks, you have servers, RAID arrays. We collect different metrics, and we have a system that we started programming in 2007, I think. It's from the design point of view not much different than what Torben presented a few minutes ago. You have data collection agents. We have agents for InfiniBand network, for our NetApp, for DDN controllers. For Lastre, we parse the proc stats and put all of that in a database. And we also create on-the-fly derived metrics from the data, so summing up all OST, throughput, and stuff like that. And it also has a request interface where you can get data. What we also do is collect Slurm log files and try to put the user jobs into clusters, and then try to correlate those clusters with all the metrics that we collected. I come back to that a bit later. So as we collect all the data, and we have our own system for a while now, we also have a live monitoring. So this is something like a live view for the admins, where you see all your OSTs and all your LANs. That's basically not the OST display, but the NetApp display, where you see all the LANs, how many IOPS, how many, what the bandwidth, total bandwidth, and the OSS servers, the InfiniBand. That's for the first phase of the system. What's currently installed, it looks more like this. Not sure if anyone can see anything, but you see everything's black. On the right side, this is phase 2. There was no I/O going on when I did the screenshot. But basically, this helps the admins to figure out what's going on. You would immediately, so we color code basically. So for each counter that we put on each rectangle, we have the maximum value where we think, what would be 100% for this counter, and you would immediately see if someone is creating files and or if their InfiniBand ports are overloaded or things like that, that would immediately show up on this display. So whenever someone is doing, small random I/O, you would see that there is no bandwidth on the NetApp, but lots of IOPS, and it immediately tells you what's going on in the system. So for our OSTs, on all the metrics we collect, we have about 75,000 MySQL tables that we feed in 5 to 10 seconds with one data. To actually know when we did collect data and when we have gaps in our data, we also record all the zeros. I haven't yet found a good way to distinguish between failures of data collection and getting rid of the zeros, or a good way to getting rid of the zeros but still being able to figure out that I did collect data during that some point in time, and with something like SQL. I don't know how to do this. You would probably need for each for each table an additional table that tells you whenever the data collection was active. So that's, I don't know, something we have to figure out. And if you want to look back over 6 months, then that's 4 terabytes of data. So that's nothing you want to look at in a serial approach. To actually analyze the data, what we do is we map operators to tables, to all these tables, and hopefully in parallel. It's timestamp normalization. Then you do align all the timestamps. So because over time, your timestamps on your data collection will shift. So you will have a little bit of gap between different nodes whenever they collect, and you have to align them, and then you can sum them up or compare things like that. You can't just do it without aligning them. And finally, we put them. Last week, a student got done with some work in Swift T. This is a kind of data dependency language where you can describe data dependencies, and you have a compiler that compiles that in an MPI program, and you can start it on as many nodes as you have, and it will do all the tasks in parallel. So we have a very small binary that does basic things like it has all the operators in it, and we run it on the tables in parallel. And then for summing up like hundreds of tables, it will create basically a tree, and then it will be done in logarithmic time. From the original data, we are creating derived metrics. So some metrics, for example, are average I/O sizes, and also how balanced the OSTs are accessed. So you want to know if some user is really running against a few OSTs and not using them all. What we also do is no, it's not what's coming a bit later. This correlating all the metrics that we have with jobs from users. So this is one of the metrics I sometimes look at. The x-axis description is wrong. It's a sum of all. It's a bandwidth sum on the NetApps versus the bandwidth as reported by the OST, and you can see there is quite a difference between what for all the LANs the NetApps see on bandwidth and what the LANs report on bandwidth. So I haven't looked into that, but this is actually why we keep all the data for in full resolution a long time. Is this is in 20-second interval. If you look at it in a 60-second interval, there's a lot of information gone. If you look at it in 10-minute intervals and look at the sum, then it's basically over. Yeah. you would say everything is okay. There is a factor of kind of 2 between the I/O that you see in the NetApps and the I/O on OSTs, and you can try to figure it out. And yeah, that's probably then would lead to some wrong conclusion. So another interesting thing I'm looking is bandwidth versus IOPS. So sometimes you have times. So you see the nice 1 megabyte line, but it's basically your biggest I/O size. So this is basically for each 10-second interval, you point 1 dot IOPS versus bandwidth for that interval. And there are some, and what I then do is I take those, outliers and take the timestamp for these, and then look which users have been running stuff there, and not at other times, but only at these times. And then I, talk to them. So I/O and job correlation. So to actually be able to correlate user I/O to more or less anonymous statistics like bandwidth on the file system, or CPU load on a storage controller, or cache usage on a storage controller, we are splitting the user activities into classes. So because one user, at least in our environment, they do things for a while in the same style. So they log in, they program some code, and then they run production. And that production run is typically, most of times it's a binary, same binary with a similar data set size, so they have similar run times, similar I/O characteristics, and then they, after 2, 4 weeks, maybe half a year, they stop, write a paper, and then they come back and do something, different, slightly different, maybe the same stuff again. But what we're trying to do is automatically create job clusters from this behavior, and then try to figure out if those job clusters match to peaks in metrics. So this is 1 week of bandwidth and 1 week with the allocated cores in the system, and it's actually 100,000 jobs that are in this picture. And so we define a job class by similar runtime, and it's same user ID, same user, same number of processors, and then a similar job start time. And there can be some gaps, if for weekends and stuff like that. But if the user didn't run stuff for 2 weeks, we basically start a new job cluster for our analysis. And to actually do this, we take all the jobs, sort it by runtime, and then apply clustering algorithms. The nice thing is that if you look at, if users complain to you that something's wrong with their jobs, they're running too long, you can take a nice look. You can cluster their jobs and see, in what clusters they are split up, and then talk to them and see what they would expect it should look like, and versus what it really looks. From this picture, if you apply this technique, you can figure out a cluster of 77 jobs that are actually responsible or correlate very well with the bandwidth peak that we saw in this week. So basically, for each job cluster, we then correlate, or we calculate a timeline, how many cores this cluster has allocated, and we correlate this with the metrics. So how I'm doing in time? Oh, okay. So to actually, gain something from this, you have to take all your metrics, all your job clusters, and run cross correlation with all of it, and that takes some time. And at the end, you get like a histogram of all the correlations for this case, and the three bars on the right are actually usable data. The rest is, no correlation between this metric and this job of clusters. So you then take whatever correlation you found, and which has a high correlation factor, and then look which metric correlated to what job class, and see how many jobs are in there, and then start to talk to the user. So something we don't know how to do is Lustre has nice histograms, for example, I/O sizes. And if anyone has a nice idea how I can put that in a database, that would help. Currently, I have for each different size, I have one table, and it mostly gets filled up with zeros. That's not really efficient. Then a nice way to deal with the zeros would be helpful. I could probably record for each data source when it was active and when it was not active. That's not really helpful. So if there is a good time series database that can deal with that kind of things, where you can mark gaps in your performance data because they didn't record anything, that would help. Other approaches than this SwiftT, there is a tool called Flink. It's also an Apache top-level project where you can do similar things as with SwiftT. So basically describe data dependencies and then give these kind of primitive operations on your tables to Flink, and it will automatically run that workflow over your tables. And another thing would be to cache intermediate results. So because things like the bandwidth on the file system, something like minimum and average or maximum bandwidth for 10-minute intervals or something like this you can use very often. But currently I have not found a way how to, once I extracted this in my workflow, to store it somewhere, these intermediate results, and whenever the workflow comes to the same point and needs the same graph again, currently it will compute it again, but I wanted to take it and not do it again. What we did is map anonymous performance data back to user activities. One reason why we did this is because we're running Lustre 2.1. So the 2.5 was just installed beginning of the year. We still need to incorporate job stats. I don't have a good idea how to put job stats or job ID based performance data in our concept. So and use that somehow. Would be nice to have that, because that would release the burden of figuring out what each job actually does, because you would know it. And we would really like to advance towards more into look more at the hardware. So there is different type of hardware that will show up. There is a project from Seagate that's called Kinetic. I think they have already open sourced the drivers for this, where disk is basically stored key value store. We want to try these kind of things and see how this can be used for our workflows. We also want to try with our system to use other storage approaches for our users, for example, putting metadata and key value stores. We have one user that writes HDF5 files with lots of metadata in it, and it would be nice if that could go to some scalable key value store, maybe on an SSD somewhere, and we would get rid of a lot of small file IOs, I think. Slide number 289. That's cool. Okay, that's it. Questions?
Anybody? So, Michael, back when we had our DDN 9550s, I was really quite impressed with the tool that you guys came up with to sort of, measure bandwidth on the controller. And, frankly, I was blown away by what you just presented in terms of, live monitoring. I mean, pretty colors.
Oh, yeah.
I think that management will love to see that. Is this available? Is this something you want to make available?
Yeah. So the tool is open source. Currently, it's on we have Fusion Forge server. So basically, SourceForge, copy of the SourceForge software running on we host a few projects there, and this is one of them. But it's open source. Yeah.
Okay.
It's a GPL license.
I didn't see the URL on slides. Did I miss it?
No, I did a mistake by not putting it on there. You're right.
If you could find a way to slap it in there so that when we load it to the site, people going through your slides will be able to see it.
Yeah, that's easy.
Cool. Anyone? Michael, thank you very much.
Welcome.